Hey guys, so today we're going to be talking about knight stours in the context of competitive programming. So if you're into programming, you've probably heard of, or into programming and algorithms, you've probably heard of the term knight stour before. Or if you're into math, you might have also heard of this term before. So if you play chess, you'll know that a knight is just a piece that, say this is the chessboard. Then the knight can move, say the knight is here, it can move like this in an L shape. So one block across and then two blocks up or down. So if you don't play chess, it's just the piece that looks like a horse. I'm sure you've seen it before. And in the context of competitive programming, a knight stour is just a sequence of moves on an n times n board. So on a square board, such that the knight visits each square exactly once. And a knight stour is called an open tour if it ends up on a square different from the square it started in. And for a closed tour, it's where a knight ends up on the same square it started in. So if we draw like a chessboard, we can demonstrate. So if I can draw a proper chessboard. Okay, it's not very straight, but yeah, you get the point. So one way to construct a knight stour is through backtracking. So if we recall what backtracking is, it's basically using recursive function calls. So like we can try here, and then if there are solutions, so there's a function that checks for possible moves, right? Now, to check for possible moves, it calls itself for each of the squares that it lands on. So say if we start from here, then through backtracking we can just check. So the knight starts here, and then there are two possible squares that the knight can move to, and it calls the same function for each of these squares. And then if there is a result, then it just keeps calling it for the possible squares, and then etc. And then if it comes to a dead end, it just backtracks. So yeah, that's basically what backtracking is. But this, if you probably know that backtracking for large inputs, it doesn't have that great of a time complexity. So it can be, there's an algorithm that you can use to find a knight stour on a square board. It's called Warnsdorf's rule. I'm not sure if that's how you pronounce it, but yeah. So say a knight starts here. Oops, let's draw it better. Okay, say the knight starts here, and then Warnsdorf's rule basically says that well, you can to find a knight stour in a square board, then you can always visit the square where there is the least number of choices. So from here, the knight has these 5 or 6 positions that it can move to, and it picks the square that has the least number of possible squares that it can go to. That probably makes no sense. So say like if it moves here, then it only has one possible square to go to, which is here, right? It can't go back. It can't go back because it's already been visited. And if it visits here, this square, then it has 1, 2, 3 squares that it can visit to. And from here, it's 1, 2, 3 squares it can go to. So we want to minimize that number. So in this case, we can go to either this one or this one. Both of these have only one place to go to, so we go to either of those. And then let's say we move here, and then right now it has only one place to go, so it moves here. And then right now it has 1, 2, this is becoming messy, 3, 4 places to go, and then it just picks the one with the least number of choices, which happens to be this one, I think. So yeah, it moves here, and then only one choice left, so here, and etc. You get the idea. So yeah, this is what a Knight's Tour is, and this is a basic algorithm to help you find a Knight's Tour on an n times n board. And this algorithm also works for really big board sizes, so yeah, it's pretty optimized. It's better than backtracking. So goodbye, hope you learned something today, and see you later.